Anybody need this front line? Okay, so today we have one purpose only, and that is to do what we can to get you all ready for the test coming up on Tuesday. So repeating the information that was posted before, I have, as you've seen, if you've turned in the homework 4 quiz, that has already been graded. I've made a lot of progress grading the rest of homework 4. With any luck, maybe tonight or certainly by tomorrow morning, that will be done too. And then this part I also will put out there sometime tomorrow. Okay, so what I'm going to do is give some general information about the types of problems that you can expect on a test. In other words, as much as possible, a step-by-step procedure to follow. And then we'll look at whatever you all want to look at, like taking questions on the practice test, etc. Okay, so... Okay.
Send the concept check answers in the same email that I send all the other stuff.
I'm sorry, what?
The concept check.
Yeah.
If I send that in the same email as I send all the other work, is that fine? Or do you want me to submit it to the?
If you include it with the rest of the assignment, that's fine.
Okay.
Yeah.
So I think I did that once before.
Yeah, and actually, before I started using Canvas, that was how it was done. So, okay. And just to make sure everybody's aware that when I post the grade for homework in Canvas, so that includes both the whatever explorations there were and the concept check score. So, like for example, I'll give each concept check question a certain number of points, and then a certain number of points for each exploration. But explorations will be worth more, and all of that's made out of 100 for your overall grade. Okay, now types of problems. I'll emphasize this is the regular problems. Okay, actually, let's make this a little bigger. Okay. Okay. So there will be 5 of these regular problems on the test. So I'll say something about each one. Okay. So bounding the interpolation error for given function, given x values on a given interval AB. Okay. So what's done there is okay. So we start with the interpolation error formula, and this is given on the formula sheet. Actually, I'm going to be lazy.
Are you saying this is the sheet that you were providing?
Yes. Okay. Oh,
Didn't realize that we were gonna have a formula sheet.
oh, okay. I did talk about that, but that might have not have filtered its way down here. Yeah, it was something I discussed in class. That if you look at the practice test, so did you see it there? That. Yeah. So.
I didn't know we were gonna have that on the test.
Oh, okay. Yeah. So, yeah, what you see here, you will have in front of you. Yeah. Okay. Um, so what this entails, I guess, as this is your starting point. Okay, let me get back to the notes. Okay. Something seems off here. Okay. So you substitute in everything that's given. X, n, which is always number of points minus 1. Okay, so in other words, if this is a quadratic, I'll give you free interpolation points, so n would be 2. Okay. Okay. Number of interpolation points minus 1. And the given x values are all also filled in there. Okay, and then next, find the maximum of an absolute value, whatever derivative comes up. On the interval AB, and also find the maximum of, again, absolute value, x minus x naught, x minus x1, x minus xn, also on AB. They have to be done independently of each other because this part is evaluated at some x in AB, whereas this point is unknown. So we can't treat it all as one function. Then again, most likely easier to have upper bounds for the two of these pieces separately. Once you have those maxima, then those will be numbers. Then you'll just put those in here, and you're done. So that's okay. So your answer is the product of these maxima, and then just the n plus 1 factorial. So divided by that. Okay. Okay. Now, as far as in both cases, steps 3 and 4, this usual procedure as taught in Cal 1, using critical points, etc. Okay. Now, this is something that's brought up in the solution that I'm pointing out here. Can anyone tell me, actually, well, this was discussed before, when you're finding the maximum of a function on some closed interval, you're supposed to check for critical points, and what else are you supposed to check for?
Endpoints?
Yes. Can anyone tell me why that is not necessary in this case? Okay, well, actually, let me clarify the question. Why is checking endpoints not necessary when the endpoints are chosen from the xi? That part's important.
Functional harnesses.
Yes, because well, yes. What happens here? Yeah, okay, so now I should mention this only applies to step 4. So here, and what I would do is I would choose the interval so that it's just the interval, whatever interval contains the interpolation points, like x0 and xn. Yeah, so at those points, at the endpoints, the function's 0. So you're definitely not going to find a maximum there. Whereas for step 3, no dice. You still have to check the endpoints for that one. But here's another potentially time-saving tip. This would only apply to step 3. If you happen to know that this, whatever n plus first derivative you have, is always increasing or always decreasing on AB, then all you would have to do is plug in one of the endpoints. So as an example, take sine x. If your derivative turned out to be sine x on the interval 0 to pi over 2. Now, for those of you who've forgotten your trig, sine of 0 is 0. Sine of pi over 2 is 1. So sine is increasing from 0 to pi over 2. So you want the maximum, you just plug in pi over 2 and you're done. So there are cases like that for certain functions. You know if they're increasing or decreasing. You should state that so you're not. I don't know you're just guessing, or so that I know you're not just guessing. So that saves you the trouble of dealing with critical points, because in that case you're not going to find any critical points anyway. Okay, so potential time-saving tip. All right. So any questions about? Let me zoom out a little bit so we can see everything. Okay, about what to do for this kind of problem. So this is the first one on the practice test.
You skip like a couple steps on both of them. In the book, you skip step. And
What?
On the practice test, you skip step.
Tell me what I skipped.
Because you move from right here in the book.
Okay, you mean the example?
Yeah, in
Well,
your example.
Well, because
So
I'm talking about general procedure. So
So I know you derive the answer, but I don't know how you come to get to it. I
Okay.
know the answer.
okay, I mean, what I gave does not. There may be a certain level of detail we can talk about, but again, I'm describing a procedure that's supposed to work for whatever I give you. So that's going to cause some lack of detail. I'm not leaving out anything, so don't talk to me like that. Okay, I'm going to get this error analysis. Okay, so you're saying in the example, this one right here.
7.242.
Yeah. Yeah, so I filled in the particulars right here. These are the 2 points. And then, so actually this case here, if the points go from 0 to 1, so in that interval, sine is, okay, so it's increasing. So if we're looking at the absolute value, we'd forget about the minus anyway. So this is exactly what I was just talking about, that this function is increasing on the given interval, 0 to 1. So you can just plug in, so the maximum absolute value would just be sine of 1. And then here, also what we were just talking about, now you have to bound this part from the error. And it's noted that at the endpoint, it's going to be 0 anyway, so we can forget about that. Okay. Now, yes, I didn't talk about the process of taking the derivative and finding a critical point, because this is a numerical analysis textbook, not a Cal 1 textbook. Presumably a student reading this book would know how to find a critical point. But that's what you would do, is you would take the derivative of this, x squared minus x, the derivative would be 2x minus 1, which is 0 at 1/2. And then, following that normal procedure, that 1/2 has to be plugged into here, and that's where we get the 1/4. Yeah. So yeah, I'm glossing over the little bit of details of how you find a maximum. But that's a lower level skill. Okay. But yeah, so that procedure that I described in the notes is laid out here. Find a maximum of this in absolute value, maximum of that in absolute value. You have to throw in a factorial, and there you have it.
So the 1/4 is epsilon, right?
What?
The 1/4 is epsilon. Is that what you plugged that in?
Oh, well, I'm not sure where the epsilon's coming from, but
Or the right next to the e or the e.
Wait.
Alright, it looks like there's an epsilon times the e to the x.
oh, wait.
There's a sign. The sign.
Yeah,
Oh,
it's
this?
arrow.
Yeah.
The arrows.
Oh, okay. Yeah, so the unknown point is labeled as xc of x, and that's because it depends. Whatever this unknown point is, that would happen to give the exact error. That point depends on x. But all we really know about this whole expression xc of x is it's in this interval, and that's why we find the maximum, so we're covered no matter what. Yeah, there's yes.
When we're bounding the arrow, does the sign, does it have to be strictly greater than or equal to, can it be less than that? Because in the example you have less than or equal to. So can we have the case where it's just strictly less than?
I'm sorry. It's a connection. I'm having a great deal of difficulty understanding.
In the example you have in your textbook,
Yep.
the arrow bounded less than or equal to sine 1/8.
Yes.
Is it possible to have just less than value on your bounding the arrow?
Oh, I mean like bounding it by 1?
No. I'm talking about inequality. Can it be strictly less than instead of just less than or equal to?
Oh, I see. Okay. It's really best to stick with less than or equal to, because although remote, there's still that possibility. Just because we're finding maximum of anything, that inherently is a less than or equal to. But either way, what we're looking for is an upper bound, and we have that.
So that difference just difference between maximum.
Yeah, because also, yeah, it is because well, as long as we're going to get into real analysis terms, which might make some people unhappy, but we're on a closed interval. A continuous function on a closed interval has actual maximum. So we have that. So we know that's what we're getting. If it was an open interval, that'd be a different story.
And the sine 1/8. The 8 is from the 2 factorial times the half or x.
Okay, it comes from, there's a 2 factorial, and also the fact that this part is less than or equal to 1/4.
Oh, so yeah, okay. The 1/4 times the 2 factorial.
Yeah.
The exercise you gave in the textbook, question 7.4.2.
Okay. Of this one here?
Yeah.
Okay.
So when trying to bound the product of the x and when we found the critical point, we didn't get a rational solution. The roots were not rational. So how do we bound them?
Well, you could just it's fine to take a decimal approximation to like a few decimal places, and that's fine.
Yeah, that's the reason why I was asking about the strict inequality. Since we are using an approximation, can it still be less than or equal to?
Yeah. Well, the thing is, all we're looking for is an upper bound. It doesn't necessarily have to be the absolute least upper bound we can find, because we're really not going to get that anyway. So, if you want to make sure that it's an upper bound, round up. Yeah. And actually, that's actually why I worded this way on the test. Obtain an upper bound. Now, I still want you to follow this procedure. Like, if you want to simply write down the error is less than or equal to 100 and move on, you'd probably be right. That's not what I'm looking for. So it's got to be a useful bound. And like for example, okay, here's something that I would accept. Here we have actually the example is a better one to look at. Here, having to bound this, we're on the interval 0 to 1, so we end up with this. But if I'd given this problem on a test, I would have been perfectly fine if you're saying, well, sine is between -1 and 1, so you can bound it by 1. So that's reasonable.
There's reasoning behind.
Yes. Yeah. So if you can explain what you do, that's good. All right. Are there any other questions about this kind of problem before we move to the next kind of problem? Okay. Next. Dealing with a floating point arithmetic issue. And there are two issues under consideration, so I would pick one of them. So it could be catastrophic cancellation, or, overflow. So you had both of these on homework 3. So what you're doing is you're modifying a given expression to work around whatever issue it is. Okay. Now, so what's happening here is in a problem. If we look at a problem on a practice test. Okay, so this is something where catastrophic cancellation comes up. So here, you actually evaluating it using 5 digits. Now, when I give a direction like this, okay, so I'll make a note here of that. Okay. So if evaluating an expression with, say, k-digit arithmetic, what that means is, so round to k digits, whoops, that's lowercase k, digits after every individual computation you do. So in the case of, and that's actually what was carried out here. So it was a 5-digit system, so you can have 5 significant digits in every single number you write down. So now, technically, a square root involves multiple floating point operations, but for the sake of this test, we'll think of it as just being 1, because you're going to punch one button on your calculator. Yes, you should have a calculator with you. So here I've represented every single intermediate result by rounding to 5 significant digits. And what we get here is 1, whereas if you were to evaluate the same expression, here you'd be using whatever full precision is available on your calculator, and we see that it's very far off. So why is that? And if there's subtraction going on, that's the sort of thing where you're looking at catastrophic cancellation. Whereas if the issue was overflow, it'd be something where you just wouldn't be able to get a result at all. Like you would get a number that... so I'd have specified not just number of digits, but also what's the maximum magnitude allowed. So it can only be overflow if a maximum magnitude is specified. In other words, the u in a floating point system, the upper bound in the exponents. I didn't specify that in this problem. I just said 5 digits of precision. So overflow could not have been it. The L, the upper exponent, that would indicate, that'd be something that would lead to an indication of underflow. But underflow is not really a big deal because you could always save a result as 0. So we're not going to deal with that in this problem. Okay. Now, once you've identified what is wrong with the expression from a floating point arithmetic standpoint, what can you do with it? So algebraic techniques for modifying expressions. Here are a few, not meant to be an exhaustive list, but it gives you the idea. Put over a common denominator. That actually came up on homework 3. You had that 1 over 1 plus x minus 1 over 1 minus x, or I think it was vice versa, actually. Yeah, it was vice versa. And you put everything over a common denominator, and that eliminated cancellation error. Multiplying and dividing by the conjugate. So you have an expression involving square roots. So that turned out to be what worked in this problem. So we had a difference of square roots. So the conjugate is when you take a same expression but change the sign in the middle. So multiplying and dividing by conjugate and then simplifying, taking advantage of what the conjugate gives you, because now you end up with a difference of squares where things will cancel out. So here the cancellation occurs on paper before you do any floating point arithmetic. So you're not going to have error resulting from it. And then simplifying as much as you can. So now the subtraction that was a problem before becomes an addition that has no problem at all. That also came up in the homework for the fixing a quadratic formula. Okay. And then also this one applies to overflow. So factoring. So there's a problem in the homework 3 about like z is the square root of x squared plus y squared. So basically by factoring out the larger number of the two under the radical, you get an expression that avoids overflow. So algebraic techniques such as these. Number one, just because it came up in an example I did in class. Trig identities. I will not put you in a position of having to spend time studying for this test memorizing a list of trig identities. So if something like that comes up, I will provide appropriate information. But these are the kind of things you can do to rework an expression. Notice it says here, after modifying, repeat the computation again using. Okay, well here I specified chopping instead of rounding. So, so sure enough, this answer turned out to be correct to 5 digits. not sure why I said chopping instead of rounding. I wrote this problem many years ago. So I wonder if something fails in that case. But okay. So that's the idea, that you... so given an expression, identify the issue. Which is it? Is it cancellation or overflow? Modify the expression, and then go from there. Now, another important point to make. So whatever issue it is, they don't occur all the time. These expressions are functions of various parameters. Like, so for example, so in the practice problem, the given expression only had a cancellation issue when h is near 0. So it only has to be fixed for that case. So you're just focusing on that. If it ends up having a problem elsewhere, that's okay. Like, for example, the homework problem, on homework 3, we had 1 over 1 minus x minus 1 over 1 plus x. Now, that kind of expression, no matter what you do to it, is problematic at plus or minus 1. The whole thing's undefined. We're not dealing with that. That expression had cancellation error for x near 0. So you fix the problem when considering x near 0. Okay. So don't broaden the scope of a problem. That's what I'm saying here. Okay. Questions about this kind of problem? Okay. Third kind of problem. Convergence as h goes to 0. And actually, I'm just going to narrow it down to that, because we did study two types of convergence. N goes to infinity, or h goes to 0. H goes to 0 is what was put in the practice test. It's what will be on the real test also. I'm doing it out of laziness because it's easier to talk about. Okay, so what happens in that case is so basically you use Taylor series to substitute for any non-polynomial functions. So such as e to the h, cosine h, sine h. Okay. It occurred to me, let me take a look at the practice test itself. Oh, wait, I have that here. Okay, if there is a need to provide certain Taylor series on the formula sheet, I will do that. I didn't have that on the original formula sheet, but if it's necessary, I'll put that there. Okay. Now, a thing to keep in mind is be careful about how many terms of a Taylor series you use. Make sure you have something that doesn't cancel. So for example, the one in practice test involved exponential, and it also involved cosine. So there were two Taylor series that were substituted in. Okay. And the thing is, we have like the 1 from e to the h cancels with the 1 for cosine. So you definitely need to go further than that. You also had okay. Yeah, let's see, what else did we have here? We have a h right here. But also, because the limit was 1, I rewrote the 1 as h over h. So this is where we're trying to see what happens. This is where we're working with our Taylor series. So notice there's an h in the Taylor series for exponential. It cancels with the h over here. Notice we also have a h squared over 2 here and a plus h squared over 2 here. Cancels with the h squared here. It's only when you get to cubic terms, this one for exponential, and then we have a 4th degree term for cosine. That's when you have items that are not going to cancel, and that's what your rate of convergence, that's where you're going to get it. From whichever terms in your Taylor expansion are not canceled by something else. So be sure to go out far enough so that you get something that doesn't cancel. So in other words, suppose I had stopped here for the exponential and stopped here for cosine. Everything would have canceled. That means you didn't go out too far, or it didn't go out far enough. Okay. Once you get down to this point, it's really the lowest power of h that's going to win. So here I had everything over h, so I simplify that, and I get h squared. And so that indicates a rate of convergence. And all I'm looking for is the rate of convergence, so let me point that out. That's what rate of convergence is. It's expressed using big O notation. So here I went a little further than necessary because I'm actually trying to show that this is less than or equal to a constant times h squared, and even then on a certain interval. But really, once I get down to this point and I see what this lowest power is, I know the answer. So yeah, so that's where you can stop.
We would just do big O h squared.
Right. Yeah, I'm not looking for the constant because we know how it's going to play out.
Really silly question.
Yeah.
This is recorded too, right? Like even though you're here.
Yes, I'm recording this.
Okay.
Okay. Yeah. Okay. Questions about this one?
That's straightforward.
Well, okay. Well, you were concerned about time earlier, so yeah.
I like this one.
Okay. Well. All right.
The Taylor, we could probably need a Taylor on that, remember?
Yeah. Well, I think for the most part this problem went well on the homework. Although there were still a number of people who got the wrong order rate of convergence. So, it's a chance for everybody to show that they know how to do it. Okay. Okay. Now, the next kind of problem. Lagrangian interpolation with error estimates. Okay. Okay. So what you do is first form the Lagrange polynomials for given x values, x0, x1, whoops, not sure what happened there, not x1, xn. So using formula that's given on the formula sheet for the Lagrange polynomials. Okay, let me make that bigger. Okay. This right here. Now, if I were to describe this in words, so your numerator is always x. Like if you want the Lagrange polynomial that's equal to 1 at a certain point, then you have x minus the other points divided by xj minus the other points. So I would refer you. Well, we've have, of course, an example in the practice test. There's also an example in the text on how you write out these Lagrange polynomials. So let me fill that in here. For Lagrange polynomial that is 1 at xj, 0 at others, it's x minus the others over xj minus the others. So you're always picking out one of these points and all the other x values go in here, and you multiply all these together. That's your Lagrange polynomial. Do not take the time to multiply these out, simplify them. Don't do any of that. It actually makes it harder for me to grade, and you know I hate grading. Okay. Once that is done, multiply each Lagrange polynomial by corresponding y value and add them all up. So that sum is your Lagrange form of the interpolating polynomial. Okay. Okay, I don't have that on the formula sheet, but you guys gotta memorize something. But so that's the idea of forming the polynomial. And then for the last part of a problem, error estimates, it's different from the first problem. It's a little easier. Only need to find upper bound on the derivative. So, whereas you substitute a given x, because I'm only estimating error estimate at a point. So you substitute a given value of x. Not being stupid again. Okay. X into the other part of the error formula, x minus x naught minus x1, x minus xn. So at least that part of it is easier. Okay. Okay. Now, I should mention when you're bounding the derivative, as in problem one, in problem one I specify you bound it on some interval. That's true here too. You find a bound for this on the interval that contains the interpolation points. So for purposes of like checking endpoints and all that, that's where you would use for that. This came up in problem 5, that's Newton interpolation, but it's the same idea. The function was the exponential, and the interpolation points were 0, 1, 2, and 3. So you would find the maximum of a derivative of exponential on the interval 0 to 3. Okay. Questions about Lagrange form?
So why your closed interval are negative pi and pi, but not negative pi?
Okay, you're looking at the practice problem?
Yeah.
Okay.
Negative pi.
Okay, the reason I use, actually the same thing I was just talking about, the exponential. So the reason I find a bound on minus pi to pi is because that is the interval that contains the interpolation points. The interpolation points are minus pi,
Oh, I see.
minus pi over 2, 0 pi over 2, and pi.
Oh, I see.
Yeah.
Minus pi. Okay.
Yeah.
That makes sense.
Okay.
So you go as far as they could go, which is what is in the neighborhood.
Yeah, and so more specifically, since whenever I give a problem like this,
You know that magnitude is already in the neighborhood of
yeah,
negative pi
um,
to pi.
yeah, because we're doing an interpolation, not extrapolation. So this is the interval because I'm going to give the interpolation points in increasing order. I'm not going to scatter them randomly because that's just weird. Okay. Okay. Other questions about Lagrange or the error estimation for that matter? Okay. Last general procedure to discuss: Newton interpolation. Interpolation with error estimate at a point. Okay, so well, it's all about the divide differences. You fill in the divided difference table. First column is the x's. Second column is your y values, and those are your lowest order divide differences. Then go to higher order divide differences from there. So you have, like, there's an example in the text. There's also a corresponding practice problem. So write out your divide difference table because that's where a partial credit comes from. Because if you follow, like, I could look at your polynomial, your final polynomial, and be like, oh my god, that's horrible, horribly wrong. Then I look at your divided difference table and I find that of all the entries, you got them all right except one, and that just threw off everything else. Then that justifies me giving you still most of the points because you knew the procedure. You just were all thumbs in your calculator. So that table is what will save you. Okay. Once you have that, use top row of divided differences, starting from y0, and you multiply these divided differences by these polynomials. 1, x minus, then x minus x naught. Then the next one is x minus x naught times x minus x1, and so on. Each time you're adding on a linear factor, one more linear factor to then the next interpolation point, up to x minus x naught, up to x minus x n minus 1. So, dang it. Okay. So, if you have your points, x naught, x1, etc., up to xn, you will not have an x minus xn, because that would be 1 degree too high. So don't do that. The last interpolation point is the odd one out. Okay, and then add them up. So this is how you get each term in your Newton polynomial Newton form, and then just add those terms up, and that's it. Once that is done, whoops. Oh, wait. So error estimation. No difference in the procedure there, just because it's Lagrange versus Newton. That has no effect. Okay. Okay, so I may have more to add to these notes before we're done, but whatever I have in here, I will post that. I'll have all the stuff posted certainly by morning. Okay. Now, we have plenty of time. So, questions about anything? Okay, well that's good.
It's not so scary anymore.
Okay. Well, that's something. Actually, one thing I'm going to put in these notes. Okay. Things I'm supposed to do as a result of class tonight. Okay. On the formula sheet, arbitrary Taylor expansion is necessary. Also, trig identities might be necessary. Right now, I haven't actually looked at the real test in a while, so I forgot what I put on there. But
You gonna add those to it?
yeah, so depending on what the real problems entail, if in other words, I don't want to put you in a situation where you're having to spend a lot of time memorizing things that don't relate directly to the class, like stuff from lower level classes. I mean, how many of you can rattle off the Taylor series for tangent? Some of you may remember the ones for exponential, sine, and cosine. Those are the ones that come up most often, but something like that, it's out there. You can look it up, but so it's not how I want you to spend your time. Okay, so and if this is something that ends up being necessary, like for example, fixing a catastrophic cancellation case, I'll take that into account.
Do you supply the formula sheet, or is it
Yeah,
something that you write down?
a formula sheet will be literally stapled to the test.
Oh, okay.
So Dr. Cole will be here to proctor for you guys. So when I send her the test, that'll be on it. So you might as well do is as soon as you get the test, just go ahead and detach it, so you'll have it in front of you, no matter what page you're on. Okay. Other questions about the test?
Isn't there supposed to be more problems on there?
Oh.
Rather than just 5 that are on the practice there?
Oh, right. Let me. Do I have that here? Okay, let me. Okay. So the other part of the test, I mentioned this earlier, but I might as well repeat it now. So there will be 10 concept check-like questions taken from homeworks 2, 3, and let me check something here. Okay. Actually, I'm going to stop at 4. Even though Newton Interpolation is homework 5, which you're supposed to be working on. Yeah, I know. This will give me enough to work with, so I'll cut it off there. Because, yeah. Now, I say concept check like, meaning that it'll be on that kind of content, it'll be that kind of question. Do not expect it to be something where I just copy and paste some concept check questions onto a test. I might do that, and if so, consider it a gift. Well, depending on how good your memory is. So we'll see how tired I am when I'm making up a test.
If we're fairly well versed with those questions.
Yeah, then you will be fine.
Okay.
Let's breeze through the concept and get to the other part. So,
Yeah.
okay.
Well, yeah, you might want to do that and just go ahead and do those first. Get them out of the way.
Yeah.
What's the weighting? Is it like 50-50?
Oh, 60-40. Yeah, so these will be worth 4 points each. The regular problems will be 12 points each. By the way, one thing I want to point out for the graduate students, what I'm supposed to do is, in some sense, make 560 harder than 460 because, well, you're graduate students. And the way that is normally done is to, like on a test, give problems that the undergraduates are not required to do, but the graduate students must do. I just plain forgot to do that for this test before I announced the format. So the graduate students take that as a gift. You're getting the same test as the undergrads. I will correct that for the final. So I thought I'd give you several weeks warning. It might be something like there's one extra problem or something like that. And I'm talking like, something big. But
I just, all you don't take one for 6 months.
Okay.
That would be statistic.
That would definitely make the class more rigorous, but no, that's not what I had in mind. And I've not seen anyone else do that either. So. Interesting idea, though. Okay. Yeah, well, I mean, you're a teacher yourself, so you're allowed to think of these things. Yeah. Okay.
This is 30%. Midterm is 30% of the.
Yes, the midterm is 30% of the overall grade. Whereas the homework's 30%, and then the final is 40.
Oh, so midterm I only weighted the second.
Okay. Are there other questions?
Expression 7.4.4.
It's 7.4.4. Okay. Okay.
So when we do the induction at k, we start at k equals 1. What exactly do you want to show for k plus 1?
Okay.
To the power of k.
Yeah. So if we look at recurrence relation, so this is what you would use. So you would assume that this has leading coefficient 2 to k minus 1, that this has leading coefficient 2 to the k minus 2, and show that this has leading coefficient 2 to the k.
Oh, so you should get back a recurrence relation from them.
Well, not really, but you're using that. It's not in order something you're recovering from it. And in order for the argument to be valid, you have to take into account knowing that tk is degree k, this is degree k minus 1, this is degree k plus 1, what is the degree of every term that you have here? Because you only care about the leading coefficient. So you only care about the term of the appropriate degree. So knowing what the leading term is here, here, and then throwing in the 2x. So that has to be included in your argument about what is the leading term of each part, therefore, what is the leading term of the whole thing. Okay. So, yeah, that's how typical induction proof works. You assume it for k or less. So I guess you could argue this is technically strong induction. I mean, to me, induction's induction, but whatever. And then show it holds for the next. Other questions of any kind? You all just want to get out of here, don't you? Well, that happens as soon as there are no more questions or at 8 o'clock, whichever comes first. I can see it now, like, probably at least 3/4 of you like, please, no one ask a question, no one ask a question.
Still on that problem, 7.4.
Does you still have a question about this one?
Yes.
What?
So, are we retaining the TK of x and just writing the leading coefficient beside it?
I'm sorry, can you repeat?
Are we retaining the TK of x in that relation? 7 points. Yeah, when we put that, are we just multiplying the leading coefficient by TK of x?
Yeah.
Or we are expanding TK of x completely?
Well, so here's one way to put it that might answer your question. Okay, so okay, 7.4.4 can assume that tk of x is equal to 2 to the k minus 1 x to the k plus lower degree terms. Or more concretely, let me put it this way: 2 to the k minus 1 x to the k plus some polynomial which I'll call q k minus 1 x, where q k minus 1 is a polynomial of degree k minus 1. Whoops. All right. So you're allowed to literally write this in there. So that way it makes it clearer, because what you want to use this to obtain something like this: t k plus 1 is equal to 2 to the k x k plus 1 plus something of that must be of lower degree. Okay. So that's helpful for keeping track of things. Because I'm telling you from the induction process, you're allowed to assume tk has a leading coefficient of 2 to k minus 1. So all I'm doing is writing out what that looks like as an equation. And then this is what you show. So really, I should phrase it that way. So I should say, when I say lower degree, I should say something of degree k or less. Because you're trying to show the leading coefficient is 2 to the k. These other terms you don't know, but if you know that this is of degree k or less, that means you can ignore it. And by writing it in this form, like something times x to the k times this, where you're stating that this is a polynomial of degree k minus 1 or less, then you know what its degree is. So if you build up other expressions from things like that, again, you know what the degree is. So hopefully that helps. Anything more?
You mentioned something about cosine being 1 to 1.
Oh, okay, for this...
How do you type expression that one?
Yeah. So the reason why that is important is... Okay. Hold on. Whoops. Okay, so for 745, to show roots of tk are distinct, note that these points are all cosines of some angle theta k. Now, I'm not writing out the theta k here, but that's in the formula for the Chebyshev points that you're supposed to show. Okay. Then, okay, for some angles theta k. As I stated earlier, cosine is 1 to 1 on the interval 0 to pi. Which means that for theta 1 and theta 2 on that interval, any points on the interval, if theta 1 is not equal to theta 2, then cosine theta 1 is not equal to cosine theta 2. So, because you're trying to show that all of these cosines are distinct, but because it's 1 to 1 on this interval, it reduces the question of this one, showing the angles are distinct. Now that becomes enough. If the angles are distinct, and they lie within the interval 0 to pi, then from the one-to-oneness, you're able to conclude that the cosines of these angles are also distinct. Okay. Also, for a separate part of the question, showing if you lie within the open interval minus 1 to 1. So cosine is equal to plus or minus 1 only at certain angles. So if you show that those angles are not among the ones you have for Chebyshev points, then that guarantees that they will lie in the open interval minus 1 to 1. So that's a separate part of a question from this. You don't really have to show that these are real. They're cosines of real valued angles, so we can take for granted that they're real. So really just looking at the distinct and in minus 1 to 1 part. So to keep in mind, for what angles is cosine equal to plus or minus 1? Yeah. Okay. Any further questions?
Change your whole idea.
Okay. Anything more in the last 13 minutes? Oh, yes? Oh. Okay, I wasn't sure if there was a question or just random noise. Okay. Some of my work is on denoising. So. Okay, well, I will stick around in case those of you who are here, or if anyone wants to shout a question from Hattiesburg, but everyone else can go.